Alright, so let's take a peek at what you may have missed in class. This does give me an excuse to make up another one of these guys. So we're going to solve this problem about the Lobsterman's buoy, which is a physicist's cylinder, right? So I'm going to pretend it's a cylinder like this, and actually it goes underwater to some distance. And it's weighted down here so that it stands upright, so that our life is nice and easy. We don't have to worry too much about super difficult things. Normally, this is a depth D0 in the local water. What we'd like to do is figure out what the frequency of oscillation that this will have. The story has a shark. This is not a good shark. A shark passing by and tugging at the rope that connects the buoy to the lobster trap. I mean, this is how you find your lobster traps. And then this oscillates up and down, and we want to find the frequency of that thing. Okay, so we should think about this. What do we expect to happen with something like this? In general, with something like this, we always want to predict right away, and we'll say that something like this, we'd say something like heavier buoys have greater inertia. That's what heavier means, right? Or more weight gives you more inertia. The gravitational mass, the gravitational charge, is the same as the inertial mass in Newton's second law. So they should oscillate more slowly. And that means that frequency is smaller. Okay. So we have fewer oscillations per second or per minute or whatever for a heavier buoy. Okay, so that's good. We want to look at that. We want to check our work at the end to say that. I should have had another slide here. So what do we know? Well, we've got the buoy, and we have the seawater. Seawater, we have ρsea, but everything else has to do with the buoy. We know that it has this depth D0 when it's just sitting there. That'll be its equilibrium position. Then we have a height h, and we have an amplitude of the oscillation x, and we also know the area of this thing here. So we haven't been given the mass, but we can sort of relate it to that D0 probably. So we'll have to think about that. So let's write that down. We have a buoy, has a mass m, well, we don't know the mass, has an area a, we know its height, so if we need the total volume of the buoy, just multiply those two things together, because it's a physicist's buoy, so it's a perfect cylinder, perfect right cylinder. It has an equilibrium depth. I guess it's not a depth draft, maybe D0, and it has an oscillation frequency. No, oscillation amplitude X, capital X. And we have the sea water, which is another object, right? Object, OBJ, property, and a symbol. This is sort of like a guide, and that has a density ρsea. So when you do this on the quiz, you have to break it up into objects, properties, and symbols that go with each one of those properties. One symbol per property, multiple properties per object, and there can be objects with no properties. If it has no properties, then you don't really have to list it. Then we want to find the oscillation frequency, omega. Let's draw this. So we've got two situations that are of interest. We have the equilibrium state, where we have this draft D0. Okay. And then we have a state where we've maybe pulled this up a little bit. All right. And we still have this draft D0. This D0 is, say, this thing. So then we have a draft when we have some certain push up here, Z. So we pulled up Z. Then we have another D, the current height under the water. And that has to add up to our original draft. So this Z is the thing that's going to oscillate. This is the thing for the simple harmonic oscillator, right? So the simple harmonic oscillator has an equation, something like Z double dot plus omega squared Z equals 0. That's our standard form for the simple harmonic oscillator. This Z is the displacement from equilibrium, so that's this guy here. That's how far we pulled this up. And the D0 is equal to the current amount, the current draft here, how much of the buoy is under the water, plus that Z. Okay, so we're ready to go. That's our drawing. Now we need to analyze the problem. We need to figure out what kind of problem this is. First of all, this is an oscillation problem, so that means things are always moving, things are always accelerating, they're changing, the speed of the buoy is always changing. It increases and goes down, and the acceleration is most at the top and least when it's going through this position here. So this is a high acceleration state. This is a low acceleration state. It's actually acceleration equal to 0 at this particular point because that's our equilibrium. If we stopped it there, it would just sit there. So our concept has to take into account we have an acceleration, and that is going to be Newton's second law. If we have an acceleration, we use Newton's second law, unless we're using an energy method, but we're not there yet. And Newton's second law always has the equation, the sum of the forces is equal to m times the acceleration. And in our case, the acceleration is that Z double dot. Okay, so that's good. Good with that. And since it's Newton's second law, when we draw a representation of this, to help us with our mathematics later, we want to have a free body diagram. This force diagram says that we've got the weight coming down and a buoyant force pulling up, and there's nothing else really going on except that we've got some sort of acceleration, a Z double dot. Okay, so that acceleration is going to show up in the simple harmonic oscillator like that. It also shows up in Newton's second law, right? We have the sum of the forces, F1 plus F2, is equal to mz double dot. So we're going to use that acceleration there. All right, so what do we want to do now? We want to plan this out. We always start our plan with our target, right? Thing we want to find, this frequency of oscillation. And we do that, since this is going to be a simple harmonic motion problem, we always start the plan, well, if we're finding the frequency, we always start the plan with the standard form of the simple harmonic oscillator. All right, and we said that we're using z as our variable, so we have z double dot plus omega squared, which is this guy, so that's what we're targeting. It gets an arrow at it. Z equals 0. We don't know, we don't have any other expressions for z double dot, so we'll have to find that. And we don't have one for z, but this is something that's always going to be true. When you're finding the standard form of the simple harmonic oscillator this way, you don't need an extra equation for z. It's okay. We've got it covered. Newton's laws will fix this up for us. We'll be fine. Because what we're going to do is we're going to get this into this form and then use that analogy. Right? We're not going to solve the differential equation here. We're just going to use the analogy to say, well, this thing at the end is the frequency of oscillation. Okay. All right, so that we've done that. We only have one question mark. There's only one thing we don't know now, which is this z double dot. We already said that that also shows up in Newton's second law. So let's use Newton's second law as our next concept. That's the next thing we're going to use. And we can use the free body diagram to set that up. So we've got B. I'll call that B of z, right? Because this B is a function of z, which is something we don't know yet. But that minus the weight, which is also something we don't know, is equal to mz double dot. We also don't know m. So those are 3 question marks right there, just to find that z double dot. Okay. Let's see. We can find this buoyancy, I guess, or we can find the weight, or we can find the mass. Let's find the weight. So I actually have a really cool way to find the weight, and that's with this situation. So this situation is this thing's going up and down and oscillating, right? But we could have this situation where, before the shark started pulling things, it was just resting there in equilibrium, right? So that equilibrium, that's Newton's first law. So we can use B of 0 minus the weight is equal to 0, right? If we have z equals 0, and the thing's not moving, it's not going to start moving. If it is moving, it's still going to have a 0 acceleration. That's going to make this 0, but what this is saying is that I can use the buoyant force also as a way to measure the weight, right? And since we don't have the mass, we have to have some way to do that. So that gets rid of that guy for us. So let's cross out the question marks that we found. Okay, so let's keep on going. We're going to stay on this track, on this branch of the problem-solving tree, and find B0. Okay, so now we'll use the definition of buoyancy. So B0 is equal to ρc, the medium that's displaced. Remember, that was what we said the buoyancy was. Got the buoyancy from displacing water, and the amount of water displaced. In this case, that'll be at this situation 0 times g. So I think probably the best thing to do here is to do a d naught g. Let's not add another equation. All right, and then ρc we have, a we have, d naught we have, and g, the gravitational acceleration, we can assume. Gravitational acceleration is not going to be different than the normal value, appreciably at least. So we can just look that up. And so we've got that. There are no more question marks from this one, so we can go back to another tree branch. Let's go to the buoyancy in the Z tree branch. That's going to be ρsea times A times the current dz. So dz here, we said previously, d0 is equal to dz plus z. So dz is d naught minus z. All right, so we've got that times g. We said that we don't have to solve for z because it's going to go away in the analogy. A and ρsea we already said we had, and nothing for that guy. So we've got the bz. Then we need to get rid of the mass, and the only way I can think of to get rid of the mass would be with the definition of the weight. So W, which we've already found an expression for, is equal to m, which we're looking for, times g there. So we could find the mass that way as well. If we wanted to, we could find the mass in terms of B0. We'll try to sneak around that because it just takes, a couple of extra steps. But that gets rid of all of our question marks. Right? We got rid of the m. There aren't any left over, so we're done with our plan. Next, we need to execute on that plan. We've got all these guys here to work with. So let's go through it. We might have to start writing over this eventually, but that's okay. So when we start our plan, step A, let's go ahead and substitute 4 into 5. So that would be the buoyancy B0, the equilibrium, into the formula for BZ. So now we have BZ is equal to the equilibrium buoyancy minus the extraneous buoyancy, the extra buoyancy, or the loss of buoyancy, depending on which way Z is, due to the fact that we're off the equilibrium position. So BZ is changing, but it's changing around the equilibrium buoyancy, increasing and decreasing and stuff like that. Next, we want to substitute 3 into A, 3 being Newton's first law. That just says that this B naught is the weight. So we have the weight minus ρsea AGZ. All right. Oh, I should have marked these off, right? Mark off the ones you use. You don't have to mark off the ones you use, but it's helpful, right? It's helpful because you need to use all of the equations in your plan, and you need to use all of the equations in your execution. If you don't use it later on, it's either the last thing you've done, in which case it's the answer, then you're fine, or it's something you didn't have to do. It's something that wasn't part of the problem. So we're fine with that. Okay, go on. Let's see. What should we do? Maybe C. All right, let's go with C. How should we do this? Let's go ahead and take B and 6 and substitute it into two. All right, so we're going for Newton's second law. And let's see, 6 is this mg thing, so that's going to go over here in the mz double dot. And the b part here will substitute in the bz, so we have there's a minus w, we have a w minus a w, so we only end up with this part, so we have minus ρsea ag is equal to m, which is w over g, times z. Okay, so we're doing all right. We do want to get rid of that weight. And we found that when we use 3 and 4, we get something for the weight. So we go 3, 4, substitute that into C. So we have ρsea is equal to, what's left over? ρsea d0 times G, or Z. There's a G that would have shown up, but it's canceled there. So we've just said, well, the weight is equal to B0, B0 is equal to this thing here, S ρsea d naught times G. And then we divided out the G. So that gives us something there. And now we want to put into form of A, of 1, excuse me, this guy. So actually we're not using that yet, but put it in the standard form. So we're going to divide through by all this stuff. ρc goes away, the A goes away. Z is then equal to minus G over D naught, or Z double dot is equal to this guy times Z. Alright, so then we make the analogy to 1. So omega squared equals G over D naught, right? See, we have a Z double dot, this guy, a Z, this guy. Everything that's left over is that omega squared. That's G over D naught. So that's our omega squared there. And so G, our last step is to take the square root of F. So that's omega is equal to the square root of G over D naught. Which looks familiar. It looks a little bit like the equation for the simple pendulum, for this, the oscillating pendulum. There is a difference. This D naught is mass dependent, so that's the big difference there. The D naught is sort of not a fundamental thing about the cylinder, but it is something we can measure, and it gives us a very nice, interesting answer. Another way to have done this would be to find an effective spring constant here, right? This ρsea is like a spring constant, and then you can, we could have terminated if at that point, if I'd wanted to. I didn't really want to. So I really liked seeing this thing because it's a really simple equation. It says that the farther down you sit in the water, the slower your oscillations will be if a wave comes by and makes you start bobbing. Alright, so now we want to test this solution. Omega is G over the square root of G over D naught. The first test is to make sure our symbols are okay. So what we do is we take these symbols, G and D naught, we compare them to these guys. So G is not in this given list, so it's not given. D0 is right there. It is in the list of givens, so that goes there. The question is can I assume G? And I said I can, right? I have that little yellow dot there. So G is something I can assume. So okay, so it passes test 1. Now we need test 2. Test 2 is, are the dimensions correct? Right? So the dimensions of omega, it's measured in hertz, which is 1 over seconds, or radians per second. Radians have no units if you do it that way. Then you have the dimensions of omega are t to the minus 1. Then we want to look at our dimensions of the square root of G over D naught, which are equal to the dimensions of G to the 1/2 times the dimensions of D naught to the minus 1/2. The dimensions of G are LT to the minus 2 to the 1/2. Dimensions of d naught are L to the minus 1/2. So we have L to the 1/2, T to the minus 1/2, L to the minus 1/2. These two guys cancel, so we have T to the minus 1. So these dimensions match those dimensions. Test 2 is okay. So we've got two tests we've done for this equation. The symbols were things that we have either in the givens or something we can assume because it's a universal constant like the acceleration due to gravity. We're good with that. And then the dimensions are the same, right? The dimensions of omega and the dimensions of this ratio are inverse time. So that's also good. So we've got two tests, and so far this has passed two tests. It doesn't prove it's right, but shows that it's not wrong. Okay, that not being wrong is fairly good. A lot of times you can't tell if you're right or wrong. Most times you can't tell if you're right by looking at something. But a lot of times you can tell if you're wrong. So that's what we're doing. The third thing is, does this meet our expectations, right? We predicted at the beginning that if something was heavier, the oscillation would be slower. Is that what happens here? Now, this is indirect. So what we've got to say here is d naught is proportional to the mass, right? Because it's proportional to the weight. The heavier it is, the heavier the buoy, the lower it will ride in the water. And from this, we say omega is proportional to d naught to the minus 1/2. So omega gets smaller as d naught gets larger. And since d naught is proportional to m, that's proportional to m to the minus 1/2. So as m gets larger, you have more inertia. The oscillation frequency reduces, which means it's slower. Okay, so again, what I did there is I took our prediction. I'm just thinking about the problem in a general way and looked at our observation. Right, I've looked at the answer here to see if I can put it into a form that is similar to our prediction, and then that's why I had to do the mass is proportional to the displacement, and the frequency is proportional to the inverse of the displacement, and so on. I had to do all that to make sure that what I'm talking about with the heavier buoy is actually saying something about a heavier buoy, right? So riding lower does mean it's heavier. Yes, it does. That's true. But I had to make sure that I said that, right? Because that's what we want to do, is we want to communicate to somebody that we're not wrong. We're not obviously wrong, right? So put those two together, it's okay. This mathematically is the same as this conceptually. So everything's worked out pretty well. So what have we done here? Well, we've gone through and we've analyzed our problem. We read the problem, then we analyzed the problem. Always read your problem. And then we need to do a little bit of conceptual analysis first, right? We haven't done any math. Then we come over here and we prepare to do our math. That's our plan. So we're using our concepts to tell us, well, what sort of things could we use? One step at a time. We're not trying to throw them all together into a big box of equations, shake them up, and something happens. What we're doing is we're looking at one thing at a time, one little puzzle piece at a time, saying, where should this go? What will fit into my omega? Well, the simple harmonic oscillator will tell us something about omega. All right, well, what will tell us something about the acceleration? Well, Newton's second law tells me something about acceleration. Okay, that's good. So I write that out. I make my substitutions where I have to. Right here I'm using the free body diagram. This is just from Newton's laws. When I come over here, right, I'm using substitutions from my buoy. I'm trying to figure out something about the weight. I've got two choices. I've got my definition of weight down here, but I don't know m, and I've got my equilibrium position, or my equilibrium from the buoy, right? My buoy's equilibrium. This is a simple harmonic motion problem. If there's something to do with equilibrium, I need to know about it, right? Possibly I would have been given something like what the equilibrium z is, but I'm not given what that is, right? So I have to figure that sort of stuff out. So Newton's first law gives me something about equilibrium. That's good. But now everything else is just cleaning up, right? I'm just using the definition of buoyancy and the definition of weight for finding, these two buoyancy terms and the mass term. Just the normal sort of thing we do on a Saturday night. And that's all fine. After that, I go to the math. Now, like most of the math in this class, it's completely banal. I'm just substituting things in. The interesting thing is I can use an analogy, right? Analogies are awesome. What that's saying is that I'm looking at this equation 1 and comparing it to equation E. Equation 1 was z double dot plus omega squared z is equal to 0. So these two equations are almost the same. The only difference is we have an omega squared here and a g over d naught here. So that meant that omega squared had better be equal to g over d naught. And that gave us the oscillation frequency. So that's all we really did in this problem. All right, everything's step by step. We're not throwing spaghetti against the wall. We are carefully arranging spaghetti on the wall in a predetermined pattern. Right? Maybe not a predetermined pattern. Looking for the best edition of the spaghetti on the wall. That should be sufficient. This is the sort of thing. This is, a class problem, so it's longer. There'll be a shorter problem for the quiz, but this is still the same sort of thing that you should be able to do. This is the kind of analysis that you need to be able to do to look at the more complicated problems that we're going to do in this class and that you'll do for the next 3 years in college, which are all preparing you for the much more complicated problems that people will actually pay you to solve. Okay, because nobody's going to pay you to do something that somebody else already did, right? So that's what we're looking for in this class, is to get you on that road to solving problems systematically. All right? Bye now.